All right, welcome to the Explainer. Today we're going to jump into something that's really at the heart of calculus. How in the world do you find the slope of a curve at one single, specific point?
Okay, so think about a straight line for a second. Finding its slope is super easy, right? You just grab 2 points, do the classic rise over run, and bam, you get a number that's the same everywhere on that line. But a curve is a totally different animal. Its steepness, its slope, is changing constantly. Our trusty old formula needs 2 points, but we only have 1. So how do we even begin to tackle that?
And that right there, that's the big puzzle that differential calculus was basically invented to solve. It's all about figuring out how to measure change for things that are, well, always changing.
Okay, enough with the theory. Let's make this concrete. We'll use the classic parabola, y equals x squared, and we're going to try to find the exact, precise steepness at the single point where x equals 3.
So, here's the problem, right? We only have 1 point. How do we solve that? Well, we're going to use a little trick, a bit of a cheat, really. If we can't use 1 point, let's just pretend we have 2, just for a moment.
So let's build this second point. We know our main one is 3, 9. Now, let's imagine another point that's just super close. We'll say it's a tiny distance away, a distance we'll just call h. So its x value is 3 plus h, and its y value is just 3 plus h squared.
Now, if you draw a line between these 2 points, that line has a special name. It's called a secant line, and its slope isn't the perfect slope we want just yet, but it's a really good guess. It's the average slope between those 2 spots.
And the cool thing is, now that we have 2 points, boom, we can use the good old rise over run formula we all know and love. The change in y is 3 plus h squared minus 9, and the change in x is just 3 plus h minus 3.
Okay, so right now what we have is just an approximation. It's a good one, but it's not perfect. But here's where the magic really happens. With a little bit of algebra, we can turn this messy-looking thing into something incredibly precise.
So let's clean this up. It looks complicated, but watch what happens. First, we expand that top part. Then, look at this. The 9s just cancel out. Beautiful. And since the bottom simplified to just h, we can divide everything by h, and look what we're left with. Just 6 plus h. So simple. So what does that mean? It means the slope of our temporary line, our secant line, is exactly 6 plus h. And that's huge, because it tells us that the closer we make those 2 points, the smaller h gets, the closer and closer our approximation gets to the real answer. And this right here, is the absolute core idea of calculus. What happens in that instant? What happens when we make h so ridiculously small that it basically disappears? That's what we call taking the limit. And the answer? Oh, it's just so elegant. As h vanishes, as it gets closer and closer to 0, that 6 plus h just becomes, well, 6. And there it is. That's our answer. The exact, perfect, instantaneous slope of the curve right at x equals 3 is 6. Period. Okay, so this whole process we just went through, picking a nearby point, finding the slope, and then taking that limit as the points get infinitely close, that whole shebang has a name.
It's called the derivative. And what is it? It's the slope of the tangent line. That's the line that just kind of kisses the curve at that one single point. It's the perfect measure of the rate of change at one specific moment in time.
Now, you're going to see this written a few different ways, so don't let it throw you. You might see f prime of x or dy dx, which, hey, look at that. It kind of looks like change in y over change in x, right? But they all mean the exact same thing we just figured out, that instantaneous rate of change. So what we did was awesome for finding the slope at x equals 3, but what if we wanted to find it at x equals 10 or x equals minus 5? Doing that whole process over and over again would be a pain. So what if we could build a machine, a slope-finding machine that could give us the answer for any point we want? And guess what? The process is exactly the same. We're going to do the whole 2-point trick again, but this time, instead of putting in the number 3, we're just going to leave it as a general x. This is going to give us a formula that works everywhere on the curve. And when you do all that algebra, when you simplify everything down, you get something just beautiful and simple. The derivative of x squared is 2x. That's it. That's our slope machine. It's a brand new formula whose only job is to tell us the slope of our original curve at any point we choose. Check this out. Let's take our machine for a spin. You want the slope at x equals 3? Easy. Plug it in. 2 times 3 is 6. It's the same answer we got before, but now it's instant. What about way out at x equals 16? The slope is 32. What about where the curve is going downhill? at x equals -1. The slope is -2. See? Instant answers, no more limits to calculate.
So let's just take a step back for a second. The really big idea here isn't just that we found one slope. The huge leap is that we created a whole new function, the derivative, that tells us the story of how fast the original function is changing at every single point. That is the fundamental power of differential calculus.
And that leaves us with a final thought. We just use this to find the slope of a shape on a graph, right? But this idea of instantaneous rate of change, it's literally everywhere. Think about it. It's the velocity of your car at one exact moment. It's how fast a chemical reaction is happening right now. Once you understand the derivative, you start seeing it absolutely everywhere.